Alright, so I am sharing. You should be able to see, and it's actually recording. I think everything is working today. So this is quiz 21, question 2. Page 1. Feel free to interrupt, as always, if I move too fast or do something you don't like. So we're working with this phenylacetylene, right? It's a CC triple bond. That's acetylene, but we've replaced one of the hydrogens with phenyl group. And in the first step, we're treating that with dicyclohexylborane. I think in the video I use 9-borobicyclononane, 9-BBN, which is another reagent that will do the same thing. The THF is just there as the solvent. It's irrelevant. And then we're doing the oxidation with hydrogen peroxide and aqueous sodium hydroxide. So I'm going to just let this be pH, phenyl, so I don't have to keep writing it out. That'll make it really simple to show the various steps. So we've got phenylacetylene, and we've got the borane. This is the less substituted end, so that's the end that the electrophile is going to be attacked by. And I'm just going to write the electrophile as E+. The electrophile in this case obviously is the boron. So the boron is over there and the hydrogen is over here, and we've got these two cyclohexyl rings, and sometimes we just write those as Cy for cyclohexyl. You could also write them as R, just so we don't have to keep writing the cyclohexyl rings. It doesn't really matter what they are. So this pair of electrons is going to attack the boron. That builds up a partial negative charge on the boron, which causes the hydride to be donated as a hydride. And since it's a concerted reaction, we want to show the transition state for that. So we still have the double bond, but the third bond is starting to break, and we're forming a bond on one end to hydrogen and on the other end to boron. We're breaking the boron-hydrogen bond. We've got our two cyclohexyl groups. So our transition state looks like that. Four-membered ring, partial negative on the boron and a partial positive on the more substituted carbon. It's actually next to the benzene ring, so you can get resonance into the benzene ring as well, which makes that particularly stable. That's called a benzylic position. And the benzylic position stabilizes positive charge really well. So the first step, the hydroboration part, is just this, right? One transition state. It's a syn addition. We added the hydrogen to one end, and we added the boron with its two alkyl groups to the other end. And it's a syn addition because of the four-membered ring transition state. The boron and the hydrogen have to come from the same side because of the constraint that they're coming from the same molecule. So then we have to worry about the oxidation step. And for the purposes of the oxidation step, this whole group that we're looking at here, right, this whole group isn't changing. That's just R. So I could actually just write it as R if I wanted to, but I'll just write it out. So the first step of the oxidation is that acid-base reaction where we deprotonate the hydrogen peroxide because the pKa is 12 as opposed to 15. So we get this equilibrium that lies towards the hydroperoxide ion. So no involvement of the boron. In step 2, we're going to attack the boron. And I guess I will just write that as R. Make it easy. So we got a negative charge on the boron because it's now 4-coordinate instead of 3-coordinate, and that's what allows the alkyl shift to go. The key step is that R group migrating onto the oxygen and kicking out hydroxide. So we change the boron-carbon bond to an oxygen-carbon bond. And make boron trivalent again. And then the hydroxide ion that's liberated in that can come in and attack Hydroxide's a stronger base than hydrogen peroxide, so this reaction is actually faster than the other one. That first step, so this is step 0, this is step 1, this is step 2, it's the alkyl shift. Right? That first step is equilibrium, the shift of the alkyl group is not. And then everything from here on in is equilibrium. But the last step, where we do the proton transfer to form the borate, lies heavily towards the BO minus. So now we got a tetravalent boron with a negative charge on it again. That's not that favorable. Instead of the hydroxide falling off, we'll kick off the alkoxide instead. So we've got the RO minus, and then we've got this HO boron. And the last step, that proton transfer, that equilibrium lies far to the right to form the ROH. So we've got this OH group here and the hydrogen there. But this is an unstable enol, so it's not going to stay that way in base. So in base, we're going to do the tautomerization, which is really kind of a separate step. This tautomerization will occur anytime you have an enol. Doesn't matter how you generated said enol. And we'll actually just be going straight back to the same intermediate that we had right before that proton transfer that I had in step 5 here. And that's step 6 if you labeled the pre-equilibrium. Step 1 depends on how you do it. And then because the negative charge is on the carbon-carbon double bond, we can write a resonance structure that has the carbon-oxygen double bond, which is more stable. And then water can protonate that to generate the final product, which is the aldehyde. Oops. No double bond anymore. And I'll just redraw that with the phenyl ring in the first. So we have CH2, CHO. That's the actual final product. So this keto-enol tautomerization is an equilibrium that favors the more stable carbon-oxygen double bond. So there's a lot of steps there. Many of them are equilibrium, just oxygen attaching and detaching from the boron, or proton transfer reactions like these guys. You could also have, instead of showing this 5th step and showing the enol, you could have just taken this anion, which is the same as this anion here, and just had it protonate at carbon directly and not shown the keto-enol tautomerization separately. I decided to show them separately just because I could.